136.8 degrees Celsius. That is the exact gap between the most extreme hot and cold temperatures recorded on this planet over a single 24-hour window this season. A thermal delta wider than the difference between freezing and boiling water. On Saturday, July 18th, both ends of that planetary balance shifted simultaneously. In northwestern South America, severe heat pushed overnight temperatures to historical highs, while a remote station in Antarctica recorded an atmospheric low of -84.1 degrees Celsius, the coldest air temperature measured anywhere on Earth since 2012. Two radical extremes, logged on the exact same day, in the same hemisphere, driven by the exact same mechanism. The cold reading came directly from Concordia Station, a high-altitude research base sitting more than 3,200 meters above sea level on the East Antarctic Plateau. It is one of only 3 inland stations on the continent occupied year-round, operating in total isolation through a 4-month polar night. Thermometers there dropped within half a degree of the facility's all-time historical limit. At those extremes, atmospheric physics encounters a hard baseline. Pushing an additional fraction of a degree lower requires near-total isolation from external heat. Yet the isolated cold measurement is not the central anomaly. The core issue, the detail that demands serious attention, is what transpired thousands of kilometers to the north on that identical date, and how a single piece of planetary atmospheric machinery produced both events. Headline reporting framed these parallel events as a bizarre global coincidence, a chaotic planet producing random thermal spikes. That framing is completely incorrect. This was not a random coincidence. It was the direct output of a highly organized, locked planetary mechanism. To understand why this matters to North Americans, one must understand how large-scale polar circulations govern continental weather patterns. The engine behind both extremes is the Antarctic stratospheric polar vortex, a massive ring of high-velocity westerly winds that acts as an atmospheric containment wall around the pole. When this vortex intensifies to extreme levels, it locks deep polar cold over the high plateau. But atmospheric energy is conserved. By tightly constricting air at the pole, the vortex alters the path of mid-latitude planetary waves, the same planetary scale wave trains that drive jet stream behavior across North America, modulating everything from winter Arctic outbreaks over the Canadian Prairies to severe summer heat ridging across the continental interior. The tension in this system comes down to precise physical metrics. Concordia sits at an elevation of 3,233 meters, where the thin, dry air contains virtually no water vapor, the primary heat-trapping gas in the atmosphere. Without water vapor, the surface loses heat continuously to space via long-wave radiation during the sunless polar winter. The only force that can interrupt this cooling is the advection of warmer, moist air from lower latitudes. In July, that warmth was completely shut out. At the exact same time, the Antarctic Oscillation Index, the key metric tracking the strength of this polar circulation, surged to an extraordinary value of plus 5.0. An index reading of plus 5.0 represents an exceptionally tight, intense, and isolated polar vortex. While this locked extreme cold over the interior ice sheet, dropping continental temperatures more than 20 degrees Celsius below seasonal normals, it simultaneously forced a dramatic wave pattern downstream. That wave pattern amplified a massive high-pressure ridge over the subtropical landmass to the north, pushing winter night temperatures above 26 degrees Celsius, an anomaly more than 23 degrees Celsius above normal. This is the central mechanism. A single, highly intensified polar vortex acts as a double-sided pressure engine. It bottles extreme cold at the pole while aggressively pumping heat into adjacent continental regions. When media outlets frame these opposing records as evidence of climate instability, or, conversely, use record polar cold to dismiss global warming trends, they miss the underlying physics. Polar cold records do not disprove broad atmospheric warming, nor are they unlinked from tropical heat waves. They are two measurable outputs of a single dynamic circulatory structure operating under extreme pressure gradients. The critical question this entire situation forces us to confront is straightforward. What happens to global weather architecture when this tight stratospheric ring inevitably collapses? And where will that displaced kinetic energy go when the containment wall breaks? Minus 89.2 degrees Celsius. That is the single lowest air temperature ever recorded by instruments on the surface of Earth, logged on July 21, 1983, at Vortex Station on the high Antarctic plateau. Yesterday marked exactly 43 years since that extreme benchmark was established. For more than 4 decades, meteorologists and atmospheric scientists used that minus 89.2 figure as the absolute physical floor for Earth's climate system, the extreme benchmark against which every polar winter was measured. When Concordia Station registered minus 84.1 degrees Celsius on July 18th, initial public commentary framed it as an unprecedented breakdown of established global baselines, a reading that somehow indicated a returning ice age or a sudden reversal of planetary trends. But to understand what actually occurred, you have to examine the historical baseline established by decades of continuous polar monitoring. The systematic measurement of Antarctic surface temperatures began in earnest during the International Geophysical Year of 1957 to 1958. Before scientists established permanently staffed stations in the polar interior, meteorologists had only theoretical calculations for how cold the high plateau could get during the 4-month polar night. When bases like Vostok, sitting at an elevation of 3,488 meters, and Concordia, at 3,233 meters, began publishing continuous daily observations, they mapped a physical climate regime unlike anywhere else on the planet. To put the scale of this polar baseline into perspective for Canadians, consider the coldest instrumented reading ever recorded in North America. On February 3, 1947, observers in the small village of Snag in southwestern Yukon logged a temperature of minus 62.8 degrees Celsius. That reading stands as the ultimate benchmark for extreme continental cold in Canadian history. Yet the standard, year-in, year-out winter operational baseline for the high interior of the Antarctic plateau sits lower than Snag's all-time historical record. The interior plateau is effectively a massive elevated desert of ice, roughly the size of Ontario and Quebec combined, isolated from marine air masses and sitting above 3 kilometers of altitude. The baseline atmosphere over this region relies on 3 specific parameters to maintain its equilibrium. First, elevation. Air pressure drops dramatically above 3,000 meters, reducing total atmospheric mass. Second, water vapor. At minus 50 degrees Celsius and below, air can hold virtually zero moisture, eliminating the planet's primary heat-retaining thermal blanket. Third, radiative cooling. During the polar night, from late April through August, incoming solar radiation drops to absolute zero. The snow surface radiates thermal energy continuously out into space. Under normal baseline conditions, the surface temperature falls steadily until it reaches an equilibrium point, where heat escaping upward matches the slight amount of heat conducted through the deep ice sheet or brought in by high-altitude winds. Historically, satellite remote sensing platforms operated by agencies like NASA and monitored alongside Environment and Climate Change Canada datasets have measured remote thermal skin temperatures, the actual temperature of the top layer of snow, dipping between minus 93 degrees Celsius and minus 98 degrees Celsius in isolated topographic hollows across the plateau. However, standard meteorological baselines track air temperature measured by calibrated sensors housed inside shelter units 2 meters above the surface. In that standardized air record, hitting minus 84.1 degrees Celsius is rare, but it sits comfortably within the known historical variance of the plateau. In fact, Saturday's reading was more than 5 degrees Celsius warmer than the 1983 Vostok benchmark. Calling a reading of minus 84.1 degrees Celsius evidence of a cooling planet ignores 43 years of continuous atmospheric records. The accurate historical context shows that while minus 84.1 degrees Celsius is the coldest air temperature logged on Earth since 2012, it represents a routine, albeit tight, operational boundary of a healthy, closed, stratospheric polar vortex system. What is genuinely out of baseline is not the extreme cold on the interior ice sheet, but the simultaneous structural response occurring at the edges of the atmospheric system. Historical records maintained by global agencies show that extreme positive surges in the Antarctic Oscillation Index, such as the plus 5.0 spike observed in late June, historically create a rigid boundary layer. In baseline decades, this kept polar air firmly trapped over the southern continent, while establishing predictable, moderate wave patterns through the Southern Ocean and adjacent continents. By establishing this historical baseline, the true anomaly comes into focus. When the system operates normally, the interior plateau produces intense, stable cold, while lower latitudes experience standard seasonal transitions. But in recent seasons, the baseline stability of the circumpolar vortex ring itself has begun to shift. The historical record shows that the background climate against which these planetary waves operate has shifted upward by roughly 0.5 degrees Celsius per decade in sensitive polar regions. As a result, when the vortex locks or breaks today, the resulting thermal anomalies swing far wider outside the historical boundaries established by the observers of 1957. Understanding this historic baseline allows us to evaluate the structural integrity of the atmosphere today. The minus 84.1 degrees Celsius mark did not break the laws of physics or set a new planetary low. Rather, it demonstrated that the high plateau can still hit extreme baseline cold when the stratospheric ring holds tight. The key historical shift isn't that the plateau is getting colder. It is that the structural boundaries governing where that cold air stays and where subtropical heat replaces it are experiencing unprecedented mechanical stress. Plus 4.0 standard deviations. That was the magnitude of the atmospheric eddy heat flux anomaly detected across the 10 hectopascal stratospheric layer between 45 and 75 degrees south during the opening days of July. It represents an energy surge so immense that atmospheric models failed to anticipate its structural consequences. Sensor arrays operated by international climate networks recorded planetary waves buckling the upper stratosphere, destabilizing the high-altitude circumpolar flow that insulates the polar vortex. To understand how the minus 84.1 degrees Celsius cold anomaly at Concordia Station and the concurrent heat records thousands of kilometers away connect, one must analyze the physical breakdown mechanism of the stratospheric vortex. When commentators attribute extreme weather swings to ambiguous global instability, they mask the precise fluid mechanics at play. The true phenomenon is a sudden stratospheric warming event driven by upward propagating planetary waves. The scientific significance lies in how kinetic energy from tropospheric weather systems travels into the upper atmosphere, physically deforming a jet stream structure spanning an entire hemisphere. The physics of this engine depend on temperature gradients and atmospheric wave dynamics. In a stable state, strong temperature contrasts between the equator and the pole sustain a powerful ring of stratospheric westerly winds. This ring acts as a high-altitude containment fence. Inside the boundary, air remains trapped over the polar plateau, radiating thermal energy out into space during the polar night without replenishment. The mechanical catalyst that disrupts this engine originates far from the poles. Enormous atmospheric features known as Rossby waves, planetary-scale undulations created by ocean temperature contrasts, topography, and massive convective thunderstorm clusters near the equator, propagate upward into the stratosphere. Under specific conditions, these waves inject vast amounts of momentum into the circumpolar current. When this wave energy breaks against the stratospheric polar vortex, it acts like ocean waves crashing against a shoreline, transferring momentum directly into the wind field. If the incoming heat flux anomaly reaches extreme thresholds, such as the 4 standard deviation event documented in peer-reviewed analyses, The westerly winds rapidly decelerate or reverse direction entirely. This forces the air inside the vortex to compress and sink toward the surface. As air sinks under increasing atmospheric pressure, it warms dynamically through adiabatic compression. Within days, temperatures in the middle stratosphere can rise by 30 degrees Celsius to 50 degrees Celsius. When the vortex wall fractures, the trapped polar air mass is displaced off the pole, while warm, moisture-laden mid-latitude air rushes in to replace it. This influx alters the radiative balance across millions of square kilometers. Water vapor and cloud cover form over regions that are normally hyper-arid and clear, trapping long-wave radiation escaping from the ice sheet. Instead of radiating heat into space, the surface begins absorbing downward long-wave radiation, driving massive temperature spikes. This exact mechanism played out during the unprecedented East Antarctic winter heat wave, documented by researchers Hu Su-tang and Seohan Lee in an April study published in NPJ Climate and Atmospheric Science. Their analysis revealed that a massive wave train, originating from intense thunderstorm activity east of Australia and propagating across South America, shattered the stratospheric vortex. The resulting high-pressure anomaly drove atmospheric rivers directly onto the continent. Across Drawning Maud Land, surface air temperatures soared more than 9 degrees Celsius above normal for 17 consecutive days. At Relay Station and Dome Fuji, local anomalies peaked at 30.1 degrees Celsius and 30.9 degrees Celsius above normal on August 5th, a thermal surge exceeding 3 standard deviations from the historical climate baseline. The authors established that large-scale atmospheric circulation accounted for 47% of the total warming anomaly, while human-induced warming intensified the event by approximately 0.7 degrees Celsius, transforming what was historically a multi-century anomaly into a centennial-scale event. When the vortex breaks, it does not merely warm the pole, it disrupts jet stream positioning across the entire hemisphere. The wave pattern that destabilizes the polar fence also parks immense high-pressure ridges over lower latitudes, trapping extreme heat while displacing cold polar air elsewhere. The same fluid mechanics that triggered 30 degrees Celsius anomalies over the Antarctic interior in 2024 were responsible for locking extreme heat over subtropical South America, while bottling minus 84.1 degrees Celsius air over Concordia in 2026. The atmosphere operates as a single coupled hydraulic loop, 15.4 degrees Celsius on June 6th. That single reading was logged at Esperanza Base on the northern tip of the Trinity Peninsula, a midwinter temperature higher than the average summer maximum across most of coastal Atlantic Canada. For nearly 3 consecutive weeks in the absolute depths of the polar winter, daily maximum temperatures along that coastal corridor stayed strictly above the freezing mark. The physical consequence was immediate. Bare rock emerged at the base of Collins Glacier. Exposed ground alters the surface albedo, absorbing solar radiation and accelerating thermal loss into adjacent ice masses. When a polar atmospheric mechanism breaks down, the resulting physical impact is not an abstract concept on a computer model. It is an immediate operational crisis for real-world infrastructure, ice stability, and human populations. To understand how high-latitude atmospheric destabilization translates into direct real-world impacts, Canadians only need to look at how extreme circulatory wave patterns alter local ecosystems, critical transport networks, and resource baselines across North America. When planetary wave activity locks jet streams into amplified configurations, the consequences cascade across municipal systems and national supply chains. Consider the physical reality of a midwinter thermal anomaly hitting coastal ice shelves. In polar regions, ice buttresses land-based glaciers, preventing vast ice volumes from sliding into the ocean. When temperatures cross 0 degrees Celsius in midwinter, surface meltwater percolates into glacier crevasses, causing thermal cracking and hydraulic lubrication at the bedrock interface. The scale of this process is difficult to visualize without a direct Canadian comparison. The total volume of ice destabilized during major Antarctic warming events spans hundreds of thousands of square kilometers, an area larger than the entire province of Newfoundland and Labrador. When coastal ice buttresses degrade, the flow velocity of upstream glaciers can accelerate by a factor of 3 to 8 within weeks. This identical atmospheric machinery, amplified planetary wave trains driven by stratospheric instability, is what triggers compound disasters across North America. When the circumpolar vortex weakens or warps, it forces prolonged blocking ridges over the continent. For residents of Western Canada, this mechanism is painfully familiar. In late June 2021, a massive high-pressure blocking ridge, driven by a severely distorted atmospheric wave train, locked over British Columbia. At Lytton, the thermometer reached an all-time Canadian record of 49.6 degrees Celsius before wildfires swept through the town. That single atmospheric blocking pattern triggered extreme glacier melt across the Garibaldi volcanic belt and accelerated retreat at the Columbia Icefield and Athabasca Glacier. In November of that same year, the opposite side of the wave pattern stalled an atmospheric river directly over the coast mountains. Over 300 millimeters of rain fell within 48 hours, severing every major highway into Vancouver, washing out Trans-Canada highway infrastructure, and triggering catastrophic flooding across the Fraser Valley. Public Safety Canada and Emergency Management BC dispatched emergency notifications via the Alert Ready system as supply lines to Canada's largest port were severed for weeks. The impact extends directly to northern infrastructure and resource management. In the Northwest Territories and Northern Ontario, winter transport relies heavily on seasonal ice roads, such as the 400-kilometer Tibbet to Contwoito supply corridor. These ice routes are engineered to support super-heavy transport loads carrying fuel and heavy equipment to isolated mining operations and communities. Operational guidelines require continuous ice thickness baselines that can only form under sustained, undisturbed winter cold. When stratospheric disturbances inject anomalous warmth into northern latitudes, the operational window for these ice roads shortens dramatically. A 2-week delay in ice formation cuts total seasonal freight capacity by millions of tons, forcing expensive airlifts that cost municipalities and industry millions of Canadian dollars. Further south, the same atmospheric blocking mechanisms drive severe drought across the Canadian Prairies, shrinking water levels in Lake Diefenbaker and reducing flow along the South Saskatchewan and Bow rivers. Reduced river discharge threatens municipal water intakes for cities like Calgary and Edmonton, while forcing BC Hydro and Manitoba Hydro to limit hydroelectric generation due to declining reservoir storage. When atmospheric containment walls collapse, the real-world consequence is an immediate shock to energy grids, municipal water supply, agricultural output, and national trade corridors. 2.58 million square kilometers. On February 26th, Antarctic sea ice reached its annual minimum extent at that exact figure, marking the 16th lowest reading in the 48-year satellite record, monitored continuously by agencies like the Canadian Ice Service and international polar tracking networks. While online commentators quickly latched onto this number as proof of total environmental collapse, and others pointed to it as a sign of complete recovery, the raw data supports neither hyperbole. What the numbers establish is a far more precise, unsettling reality. The background climate baseline has shifted permanently upward, amplifying the physical consequences whenever planetary wind patterns lock tight or shatter completely. To understand where this system is heading, we must draw a firm, honest boundary between what scientific consensus has rigorously established and what remains unresolved. What is unequivocally established is the primary thermodynamic engine. As demonstrated by researchers Hu Su-Tang and Seohan Lee in their April study in NPJ Climate and Atmospheric Science, human-induced atmospheric warming directly intensified the 2024 Antarctic winter heat wave by approximately 0.7 degrees Celsius. Under current global emission trajectories, climate modeling indicates that the frequency of these extreme stratospheric breakdown events will increase from 2 to 3 times historically to nearly 6 times under moderate emission profiles and up to 26 times by the year 2100. What remains genuinely unresolved, however, is whether the frequency of the underlying stratospheric circulation pattern itself is shifting, or if we are simply observing standard atmospheric wave patterns acting upon a warmer baseline planet. Peer-reviewed literature finds no robust trend in the frequency of sudden stratospheric warming events in the southern hemisphere. Furthermore, despite record thermal anomalies exceeding 30 degrees Celsius above seasonal normals across drowning Maudland, the vast majority of surface temperatures over the high interior plateau remain safely below 0 degrees Celsius. The immediate danger is not that the interior ice sheet of Antarctica will melt overnight. It is that the physical boundary separating polar cold from mid-latitude heat is becoming increasingly volatile. When a stratospheric polar vortex breaks down today, it does so against a baseline world that is demonstrably warmer than it was when modern instrumental monitoring began. So, how do we track this system moving forward? There are 3 specific, checkable metrics to watch over the coming months. First, track the Antarctic Oscillation Index, published continuously by global meteorological agencies. If the index remains strongly positive, hovering near or above plus 3.0, the stratospheric ring will remain locked, bottling intense cold over the Antarctic interior while forcing amplified wave patterns that steer volatile temperatures across South America and the southern hemisphere. If the index collapses rapidly into negative territory, watch for sudden stratospheric warming advisories from atmospheric tracking networks. Second, monitor the daily winter maximum temperatures along coastal ice shelf sectors, specifically near Esperanza Base and the Trinity Peninsula. If daily temperatures along coastal sectors repeatedly cross 0 degrees Celsius during polar winter, it signals that displaced warm air masses are actively lubricating coastal glaciers and accelerating mechanical ice loss. Third, observe the late-season sea ice extent reports from the Canadian Ice Service and international polar data centers. Tracking whether Antarctic sea ice growth recovers toward long-term historical medians or stalls near historic lows will indicate how much thermal energy is being retained in the upper ocean layers. Until one of those specific thresholds is crossed, the reality is clear. The atmospheric machinery that regulates planetary temperatures has not failed, but its operational margins are stretching to unprecedented extremes. The true threat of a destabilized polar vortex is not a single record-breaking temperature on a remote plateau, but what happens when that displaced atmospheric energy parks itself over vulnerable coastal ice lines and continental supply chains. Tell us in the comments below where you are watching from today. Subscribe to stay updated.